fine for you. Oh, I see. Oh, that's good. Just for fun, I just couldn't resist this transpiring. This is just a review. I'm not going to take a position or anything else. I'm just going to say what I'm finding. But I ran across this review in Reviews of Geophysics last year by Leslie Gray and a whole bunch of people you can see there. I was very impressed with that review. You don't have to agree with everything in it, but I would strongly recommend it if you want to get a feeling for all the different things you have to think about in solar physics, or solar forcing, that you take the time to read and assimilate that thing. So I'm leaving this on so you can all write it down. I don't see anybody writing it. What? Oh, you're tapping. Oh, okay. There are lots of ways of looking at solar forcing, what it's doing. For instance, I guess these are the sunspot numbers in the last 3 cycles, but there's radio, there's the magnesium lines in the chromosphere, here's the GCRs, galactic cosmic rays, this is the satellite TCI, etc., etc. So there's a lot of different ways of looking at it, and you can see they roughly tell the same story, but there's information to be gained from each one of them. This is a nice one because it shows how long the records are that we're using. These are beryllium 10. There's sunspots with funny numbers there we're not sure about. Auroras, the magnetic index, what's that? Neutrons and irradiance. So it gives you a feeling when we're trying to look back and see what the sun is doing, where we lose our records that we want to use. Reconstructions of total solar irradiance vary all over the place, and this is not for you to read all of those, but this is for you to just understand that people have tried everything you can think of, sunspot areas, magnetic, lots and lots of different things, and this is not limited to that. Oh, I put in not limited, and then you get in there. Oh well. Then finally, this is in Gavin Schmidt's review article that just came out. There's some debate over whether there's a background variation. In other words, not just up and down the 11-year cycle, but maybe there's a background variation. And the lower irradiance in the last cycle, the last few years, which probably kept us from getting a more positive trend than we were seeing, is that there is such a variation. So now we have to worry about that. In the olden days, when I was first doing this, year 2000 or so, it was really easy. This was lean 1995 or 2000, and then there was some other ones. But there was a soon-to-be large background variations. More recent things are saying, no, it's like that, with and without the background radiation. And to jump ahead, a lot of people are starting to get this answer, but not everybody. For instance, here's Hoyt and Schatten way back in '93, lean in 2000. So these were the great big ones. And Solanke and Friga, and I haven't put all the people on because this is a cottage industry. Almost anybody can play it, and they're all doing it. But there are a lot more saying this now than we're saying anything else. But for instance, here's some of the most recent ones. Steinhalber, Schreiber, I don't know how to say the G, but I'll call it Schreiber. And Shapiro, you heard Shapiro talk here just a few days ago. And here they're all saying, well, it's something like this, and look at Shapiro. So you really want to read his paper and say, what was his assumption? How did he get to that? What have you? Here are the volcanoes, but now that's bothered by the fact that we heard a talk that says you don't have to have the major volcanoes only to get stuff in the stratosphere. Other stuff can get in the stratosphere that could depress whole areas here where you have a lot of volcanoes. And that, of course, muddies the water a lot. Now, if you look at recent paleo temperatures, there are many, many more reproductions than these. The much maligned Michael Mann is here without much of a modern minimum. But Moberg and Esper and other people, here's the borehole temperatures, get it and get the others more and Dalton, what have you. I will point out that none of them get the Maunder minimum to be any higher than 1940. But we'd like to say, boy, if we really understood that, then we could pick through reasonable modeling and energy balance models which one of our solar forcings was doing it. But how well do we know all this? The data back here, the error bars are really big, and while we don't have any of these reconstructions which shows stuff way up here or way down here, that doesn't mean they're not there. We're more sure of the Maunder minimum, though. And in this particular paper by Feulner, F-E-U-L-N-E-R, somebody has done an average of what they consider to be the best reconstructions of temperature, and put in some of the latest observations of temperatures, and then put in what happens if you try to use Schriever or Shapiro or Steinhilber to model what happened. And again, here are the minimums. Here's Shapiro. So he comes to the conclusion that Shapiro's has to be an end member. It can't probably be as good as you think. In an attempt to put all this together, the paleo modeling and comparison studies, and here's a bunch of the people who are on the paper that just came out, is trying to, in the next few years, we'll be really looking at this hard, doing a lot of careful modeling, worrying about sensitivities and what have you. And you can see here names like Vieira and Krivova, people who are also working on this, Delgi, Gross. And I'll be showing you one of the things they're using for forcings, and they use all these letters, so I thought that this is introducing you. There are even more people, Munchler and lots of other people who are working on this. These are the kinds of forcings they're using, starting at the year 2000, 1740, 1500, going all the way back to about the year 800. And there's impacts of beryllium-10 in here, a lot of different things. But you can see that they're not varying by very much. And keep in mind, this is the TSI coming in, but then you have to divide that by 4 pi to get the forcing. Possible indirect forcings. People are always worried about that. Maybe changes in TSI cause indirect forcings. What about the fact that UV in the stratosphere is really a big change over a solar cycle? Galactic cosmic rays, etc., etc. This is a nice sort of summary of things that are going on. Here's the galactic cosmic rays affecting clouds, TSI, UV affecting this, and then working its way down through quasi-biennial variations, what have you. That's the UV. And then these are energetic particles that could be, there's something like GCRs, they could have an effect. And finally, there's what's called the bottom-up response. The bottom-up response is sort of fun, and I don't know why it won't show it to me. They're now showing on the screen, but they're not showing on the screen. There it is. That's what we just saw. Well, thanks to the God. No, it's not showing there either. I'll tell you what it is. It's just the fact that if you have the sunlight coming down preferentially at the extratropical latitudes, they can cause a lot of warming during a high solar activity differential. A lot more water vapor gets advected into the ITCC. That causes the whole system to get more energetic, and you can get anomalies from those things. The next graph, which first I have no idea what it will show, was showing some of the observed anomalies, the difference between the temperature anomalies in the oceans, especially the Pacific, between low activity and high activity. And while these things are easily observable, the bottom line on the bottom up and top down is they don't have a large effect on global temperatures. Small effect, but not a large effect. The other hope, of course, is that these kinds of things, especially if the models have a good stratosphere and good zoning, are picked up by the models. And we'll talk about that a little bit better. Galactic cosmic rays, here's 2 different ways of looking at them. First of all, you can see if this is percent change. They don't change very much due to the solar wind. But the other thing is, they may indeed have some effect. People are still working on it. You heard some very nice talks about that. They may still show that we're having some effect on the clouds, but there's no trend. Right now, there's a little bump here. So there's a little more trend right now because the sun is really inactive right now. And so you might say, if they're having any effect, part of this lack of rise, and it would not have been caught by the models, as a matter of fact, could be due to that. So the fact that the sun really isn't doing what anybody thought it would be doing what most people thought it would be doing in the last 5 years. But there's no real trend here, so the warming from the 80s through 2000 that we've all seen, the trend, can't be due to this. And so, while this is important to look at for a lot of different reasons, it isn't a cause of global warming. An interesting check on the models, Judith Lean's regression method, you've probably seen some of the paper, she takes a temperature record like CRU or something like that, and she breaks it into internal variability, volcanic, solar, and emitting trend. And I asked her, in fact I think we have that there, this is published, so this is the internal variability of the Earth. This is not a model, this is all observations. And the volcanoes and the solar forcing. And you can see the solar forcing there is more than you just expect for sigma t to the fourth. It's almost a tenth of a degree, not quite, at the highest variations. But there's what's left. Well, I told Judith, why don't you take the results of CCSM4, thanks to David Lawrence helping us get that stuff, and act like it's a temperature, observed record, and break it up and see what you get. And amazingly, this is the forcing she put in, and which one of those is the observations and which one is the model? Isn't that amazing? CCM4 is the light green, and CRU are the observations. So when she breaks up the data, she gets the blue, and when she breaks up the model temperature record, she gets the green. So some of these indirect effects seem to be captured by the models. It's very preliminary, we've got to do it in other things, and she's got the bit in her mouth now, wants to do a lot of different model results and see which models are doing it and which won't. And of course that'll be an incentive for everybody to put solar forcing in models. The other thing, however, is CRU doesn't show quite as much rise as the model does. If we'd done that for NCDC or NOAA or GISS, maybe we'd get more like that, but they wouldn't agree on the solar, I don't know. But there's not enough, there's no indirect forcing due to aerosols so far in these runs. Wait, film at 11, we'll see more things later. The conclusion is that about 0.24 watts per meter squared radiative forcing between the Maunder minimum and now is more appropriate than the IPCC's number. In other words, we think it's bigger than the IPCC said. Here's the range. And does still keep in mind that it's a lot smaller than the global, the greenhouse forcing. And also keep in mind that TCI changes. You have to divide by 4 pi to get the real force. More recent thinking, I wrote to Steve Lockwood and said, since Leslie Gray came out with that statement, that's an old statement, it's last year, what more has happened with Shapiro and Schreiber and what have you? And he wrote this. Essentially, he said, not enough to make us change our estimates, but enough to make us say, we still need to do more work on this. There might be something. These are really good people doing really good work, and we have to pay attention to that. Thank you.
Thank you. Just a quick clarification. Yeah, hi, Chick. Just a quick clarification. On those numbers you gave on the second or third to last slide of 0.12 or so watts per square meter, is that against the 1360 or is that against the 340?
1360.
The solar constant you measure as watts per square meter out in space on the square meter, or the solar constant divided by 4 that is per square meter of planet?
I believe that's the divided by 4.
Next question here.
Yeah, I question. So you have said that there is no variation in cosmic ray, but you have seen only the top correspond to solar minima, but if you see the bottom, there is a clear trend. So The problem is that it may be a little bit more complicated than what you have said, right?
I could get this machine to work. Let's let everybody look at that, and we can do that together, can't we?
Exactly, that is
I was trying to go faster through it.
No, it's okay. So that maybe.
There it is. Like arrow key.
Okay.
Oh. You got a good review of the whole article. What he's pointing out is that while the maximum hasn't changed, the minimum has done something funny here, although I don't know if I could make it through that.
So those minima is when they are
You can
pushing.
say, well, it's doing this, so it's not cooling as much.
So it's more complicated than what you are. It's a
Well,
little bit more
yeah,
complicated.
it's more complicated, but you also have to say, well, in that case, we wouldn't expect any warming here, but maybe we get a lot of warming here, but this is just where it stopped warming, so you know.
No, it's, yeah.
I think we'll move on to the next question.
Okay, we'll move on.
Thank you very much for the beautiful review and very comprehensive. I just have one comment about the fielded paper.
About what?
About the fielded paper. Could you please show this graph with this climate exercises once more? And there are temperature responses for a few different reconstructions. It's from the fielded paper. Because actually this paper was also discussed and Schmidt told us there are two interesting situations here. So first of all, his modeling was a little bit simple and probably adjusted to reproduce the temperature curve with volcanic forcing. So there is no surprise that the best models are with zero forcing. I mean, it's just what was written in Schmidt et al. And second very interesting thing that if you will look in the beginning of 20th century, there is a rise of the temperature. And basically all model with small forcing, exactly here. An interesting point here, so actually we're now in contact with Feller and trying to discuss this point. Just I'm finishing. All models with zero forcing underestimate this rise. And the only model which shows the proper rise is actually our model with large forcing. So now we're trying to understand why they are systematically low. So there is obviously some problem with the boundary condition. But this is quite yeah, exactly.
You're saying this?
You know, if you will look at all models, another model shows smaller, 2 times smaller rise. And so this is kind of interesting point. We now try to understand this.
Those are good points.
We'll have one more question.
Just one more quick question.
Yeah, I wanted to point out about that cosmic ray variation, which I think was the previous slide you showed. That's neutron monitor counts, and the neutron monitors only measure the high energy component that is of energy great enough to produce nuclear reactions. There are, at solar minimum, especially at the recent solar minimum, there have been...
Is that true of this
big
rate?
increase in the flux below 1 GeV. And this is a flux which produces a lot more ionization up at high latitudes. And I'm not going to talk about my own work, although it's been neglected by the Leslie Gray review. But if we talk about ion-mediated nucleation, that's a question. Yes. So, well, it's saying that there's big uncertainties that you haven't included, and I would like to see you include them in the future discussion.
If you could send me a graph similar to the one you're looking at here, or the other one, if you can send me a graph with the lower energy one, I'd love to have it. Thank you.
Okay, thank you very much, Chick.